thermoelectric is defined as a device that creates a voltage due to a temperature difference. Thermoelectrics have a low efficiency because most materials that have a high thermal conductivity have a high electrical conductivity. For an ideal thermoelectric, we need a material with a high electrical conductivity and a low thermal conductivity, which proves to be a challenge. ZT, a dimensionless parameter, is used to measure efficiency of a thermoelectric. ZT is a function of the Seebeck coefficient. Optimizing ZT often proves to be a challenge. Seebeck effect is the production of an electromotive force and consequently an electric current in a loop of material consisting of at least two dissimilar conductors when two junctions are maintained at different temperatures. It is a volumetric or interfacial phenomenon. Seebeck effect is due to temperature difference across each conductor, resulting in free electrons with higher kinetic energy where temperature is higher. At the junction of two different materials, the more energetic electrons move to create an equilibrium, resulting in a charge difference between the two materials and hence a potential difference.
Based on the potential difference, this simulation describes the movement of electrons in holes. The figure on the left is a Peltier cooler, and the figure on the right is a thermoelectric generator. Maximizing efficiency in a thermoelectric can be a real challenge.
In order to create an efficient thermoelectric, we need materials made from elements with high electrical conductivity. Unfortunately, these elements also have high thermal conductivity, which reduces our figure of merit. A closer look at the periodic table reveals that semiconductors are an ideal choice for thermoelectric materials due to their increase in electrical conductivity with temperature. Their thermal conductivity is also due to contributions from both electrons and phonons. Bismuth telluride has often been used as a thermoelectric material. Its rhombohedral lattice allows phonons to move easily. However, doping with antimony or tin or other impurities introduces defects in the lattice, which will scatter phonons and decrease the thermal conductivity of the lattice, increasing the figure of merit. At room temperature, doped semiconductors yield a figure of merit of 0.8 to 1. Scutterudites are also materials that are consisting of cobalt, nickel, or iron arsenides, which have a unique cubic lattice structure, which can accept rare earth elements that decrease its thermal conductivity. Scutterudites have produced a figure of merit at 1.4 at high temperatures. Certain oxides have also shown thermoelectric properties at high temperatures, although their figure of merit is not as high as other structures. How do we increase the figure of merit? One answer is nanostructuring. One form of nanostructuring is the manufacturing of superlattices. If we look at an N and P doped bulk semiconductor thermoelectric, the figure of merit is roughly at best 1.0. However, if we shrink the widths of these thermoelectrics to nanometers thick and create a layered structure, we can introduce more obstacles for phonon transport, as the interfaces scatter phonons but not electrons. This effect greatly decreases the thermal conductivity of the lattice and yields a figure of merit of 2.4. Although these superlattices are promising, they are difficult and costly to produce. Nanocomposites possibly represent an ultimate solution. Nanoparticles of thermoelectric materials can be made via cheap processes such as sol gel, ball milling, and solid-state reactions. They can then be compressed as macroscopic ingots with nano-sized grains. The grain boundaries scatter phonons and give impressive figures of merit, close to 3.0.
The following is a typical Rankine cycle with a boiler, pump, turbine, and condenser. The efficiency is equal to the turbine work minus the pump work divided by the heat input from the boiler. Now we are utilizing the waste heat from the condenser as an input for the thermoelectric. This is similar to the cogeneration cycle. The overall efficiency of a typical Rankine cycle is around 42%. Adding thermoelectrics will increase the overall efficiency.